Okay, well, welcome to the second talk of this last afternoon of OPAC. And I'm pleased to have Alan Knutson here to talk to us about Schubert calculus and OPACs.
Well, I would start by thanking the organizers, not for inviting me to speak, but just for letting me be here with everybody else. That's, the speaking's nice too, I guess. But I'm just really happy to see so many people. So one question that came up a couple of times was about having not just a combinatorial interpretation of something, but having multiple combinatorial interpretations. And I wanted to mention that why in particular we have multiple Littlewood-Richardson rules. So of course there is the Littlewood-Richardson rule that they originally wrote down, counting tableau, but we've heard a bunch of others. And I wanted to place them together, and you see why it's worth having more than one rule for what you might think of as the same thing. So one that was mentioned by Sasha Postnikov, or Alex Postnikov, he'll always be Sasha to me, was about the representation ring of GLN, or GLK, let me make it. So GLK of C. And this is not very interesting as a ring, actually. It's what makes it interesting to us as combinatorialists is that it's a ring with a basis. And of course, the fun is multiplying the basis elements. And the basis here is indexed by decreasing tuples of integers. And he mentioned this honeycomb model that Terry Tao and I came up with. It's in fairly simple bijection with the Berenstein-Zelevinsky triangles that preceded it. And I want to just mention another way to picture that, which is with these triangles of numbers, like Berenstein and Zelevinsky had. I've got 0 here, and then I'll have lambda 1 here, lambda 1 plus lambda 2 here, and eventually at the very top, I'll have the sum of all the lambdas. Then I'll come down this way and add on mu1 and mu2. And down here, I'll have the sum of the lambdas and the sum of the mu's. And coming across the bottom, when I want to compute C lambda mu nu, I'll be having the sum of the nu's as I go, nu1 plus nu2. And eventually, I'll have the sum of the nu's. And that better be equal to the sum of those, or else the Littlewood-Richardson coefficient is 0. One way to think about what these sums are in the representation theory sense is when you're on the irreb v lambda, the center of GLK, the scalar matrices, acts, so the matrix Z, 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 Z acts on v lambda as Z to this power. So if you tensor something where it acts Z to this power by something where it acts Z to that power, you know how that center is going to act, and that's why we only get these. Anyway, so inside, we're going to have more numbers. And the condition is that whenever you have a rhombus in here, and there's multiple kinds of rhombi, there's these, or there's these vertical rhombi. Whenever you have a rhombus, you ask that this functional that's plus on the obtuse vertices and minus on the acute vertices, that should come out non-negative. So those are the inequalities that I'm putting on the n+1 choose 2 minus 1 many entries in this guy. This is these guys we called hives because they weren't honeycombs. And it's easy to picture what this sort of functional means. If you imagine graphing this function, I mean, right now it's only a function on these lattice points, but let's extend it piecewise linearly to a piecewise linear function on, so on every single right side up or upside down triangle, I want it to be linear and affine linear. So I extend it to that, I get this continuous piecewise linear function, and I graph that. And the conditions here are that that graph should be convex. Whenever you have one of these rhombi, it should come out to break this way, not that way. In particular, that's going to force convexity around the boundary, and convexity on this side, that's these inequalities. So only if you actually put in dominant weights does it even make sense to try and count hives. And then this is a way to compute these. One thing that's special about this ring, I'd like to point out, there's a map from here to the integers called take the invariance. So it says if you have a linear combination of representations, how many times does the trivial representation show up in there? And what's nice about this functional, it lets you define a perfect pairing on here, and even a way of computing these guys in a symmetric way, or instead of computing v lambda tensor v mu and see how many times v nu occurs in there, you could take v lambda tensor v mu, tensor v nu, or v nu dual maybe, and take the invariance inside that triple tensor product. And then you get a function, sorry, you get an answer that's of course symmetric in the lambda, mu, and nu. And it's nice that the hives have this threefold symmetry that that lets you see that manifestly. So this might not be how you've learned about representation theory of GLK before, because people will say the representations of GLK are indexed by partitions of height at most k, and that's not true. So inside here, we have this other thing where we've got things of height at most k, and we've got these partitions. And these, of course, are only sort of half the story. I didn't insist that lambda k is non-negative. If I do insist lambda k is not negative, then I can take the first row to be lambda 1, lambda 2, and I get another ring that's, it sort of fits inside here and it's pretty big. And if you understand the structure constants of this subring, then that's enough to understand the structure constants on the whole ring. But it's but it no longer has this useful thing, and it no longer has this threefold symmetric way to ask about the structure constants. So what is this thing? This is the representation ring of the monoid of k by k matrices, okay? So you can think about homomorphisms from this monoid to M large, and and such a homomorphism will be determined by this, because this is dense inside MK. Of course, I only want my morphisms to be continuous, or probably I would prefer them to be algebraic, but in particular, they'll be determined by this dense subset of here. That's why this is including. But there are representations here that don't extend. In particular, the representation takes the determinant and then take the inverse. Is a perfectly good representation here. All of these are -1. It doesn't extend to this. So people, so you can say this is where the story of Tableau lives, and it's about multiplying partitions. But people very often will just say, let's consider something where we have this basis indexed by all partitions, where we don't insist anything about the number of rows or columns. And what that is, that's the representations of vec itself. So what do I mean? A representation is a functor from a one object category to vec. So here I've got this one object, which is ck, and the endomorphisms of that one object in my one object category are this group GLK. And when I take a functor from there to vec, that's exactly the same data as a representation. And I'm doing the same thing here, but here I've got, it's much more interesting to think about functors from vec to vec. I want a rule that makes sense for every vector space. Things like sim3 or alt5 or Schur functors more generally. And that's what this basis is. It's these Schur functors. And what's much nicer about this story, and this is of course really where Littlewood Richardson in terms of Tableau is ascendant. If you describe things in this way, then you don't have this number k showing up at all. And you notice that, for example, the statement, a statement like box times box is equal to domino plus domino, that's for each ck, that's ck tensor ck is alt square ck direct sum sim square ck. And it's something you can say without reference to k. So you have it's nice to have a rule that doesn't involve the k, and so you know that it works for every ck. So that wasn't working here. So this is a place where it's good to have another rule to see a different, not a symmetry property, but a stability property that tensoring Schur functors has. And the ring I'm going to talk most about, though, is this one, the cohomology ring of the Grassmannian of K-planes in N space. And actually, so here there's no N. I could take N to infinity in this case, and I'd actually get this one. So this guy has a basis indexed now by partitions lambda inside a K by N minus K box. And this one has the good property that that one has, that it again has this, this map to the integers called integrate. So you could either say I'd like to multiply 2 Schubert classes together and expand in Schubert classes, or I'd like to multiply 3 Schubert classes together and integrate. And so now I'm going to explain how to do that and see a Z3 symmetric rule on this. Yeah, you're fine, I think, on this table. So I need these 3 puzzle pieces. Yeah, okay. So there's this equilateral triangle. Ignore the shape, it's an equilateral triangle. When I, so it's going to be blue here. When I do it on the board, it's going to look, it'll have 1s on it. On the back side of those are what are going to be 0s, okay? And then these guys are 2 equilateral triangles put together and with 1s on these sides and 0s on those sides. And because on the back of red is always blue, which is going to be Grassmannian duality, if you take one of these and you flip it over, it'll still have blue on this side and red on that side. So I don't have a piece that goes red this direction and blue that direction. And sometimes just because of who was painting them at the time, red's on top or blue's on top. That's I think my children had different ideas, which was the right color to have on top. Anyway, so what you can do with these is make triangular shapes. So I'm going to make a triangle right now. How about and there's if you try and do this on your own on paper, you'll find that it's very forced. So you do get choices from time to time, but a lot of the time it's unique what you have to do. So what I'm interested in are these triangular puzzles made out of these puzzle pieces. And if we, and I'll say how they relate to the cohomology of the Grassmannian in a second, but just to observe a couple of things. So notice on this side, we've got 2 blue termini and 3 red. So N is going to be 5 in this case, and K is going to be 2, the N and K. And it's the same 2 on this side as it is on this side, as it is on that side. So it is automatic that the number of blue termini on one side matches those on the other 2 sides. That's one fun thing to figure out about the number K. Another is that this K tells me how many of these pieces there's going to be. There's going to be K squared. So there's 1, 2, 3, 4. Whereas the N minus K, 3 in this case, tells me how many of these pieces there's going to be, which will be 3 squared, 1, 2, 3, 4, 5, 6, 7, 8, 9. And therefore, just by area considerations, N squared minus K squared minus N minus K squared divided by 2 is K times N minus K, which is the dimension of this Grassmannian. So there's going to be 6 of these in this case. But we can actually do better. If you look on a single side for how many times blue is occurring counterclockwise of red. So how about I come on across this side? This blue is before these 2 reds, and that means there's going to be 2 of these pieces pointing in this direction. That one and that one. Whereas if I look on this side, say, these 2 blues are before that one red, and so there should be 2 of these pointing in this direction, and it's there, and it's there. So the puzzles are really highly determined in the interior from what they do on the outside. And so the formula here is, so I want to correspond a lambda inside this partition I'm going to correspond this to a word in 0 with k zeros and 1 with n minus k ones. And the way I do that is I come in here and I read zeros as I go up and ones as I go right. And then I leave. And that's a word. And then my puzzle pieces, as I said, are the 0 piece and the 1 piece and this piece and rotations of these. Okay, and then the statement is C lambda mu nu is the number of puzzles with lambda on this side and mu on that side and nu on that side. Or this thing I was saying here, the integral over the Grassmannian of S lambda, S mu, S nu is the number of puzzles with lambda, mu, and nu all clockwise. So this question is stated has 12 symmetries. There's 3 factorial from permuting these, but there's another factor of 2 from Grassmannian duality, that ger kn is isomorphic to ger n minus kn, and the number of puzzles is obviously invariant under that because you can take these puzzles and flip them over. And that'll tell you that, so the symmetry that's missing is commutativity, okay? Why, if I switch lambda and mu, do I get the same number of puzzles? That seems to be a lot harder. Yes. Is there any model that has all the symmetries? Yes, this one of Cartons by Hugh Thomas and Alex Young has all the symmetries. But as I recall, it's called Cartons because it's 3-dimensional. So it's less easy to play with on a whiteboard. Any questions right now? Okay, so I want to tell you a couple of applications of these and some more results we have about them, and then get to open problems about puzzles. So in fact, the way that Terry Tao and I discovered these was not to do Schubert calculus. It was to understand hives. We wanted to know if a hive exists, what does that tell you about the boundary? What are the C lambda mu nu that are not 0? That's what we wanted. Instead of actually computing them, just when is it 0, when is it not 0? And what's clear is if you add a bunch of these rhombus functionals, you'll get something non-negative. If you manage to add them up such that all of the interior dependence cancels, for example, these 2 rhombi, if I add this rhombus functional and that rhombus functional, then you'll notice that the minus and plus here cancel. So I still have more interior dependence, but maybe I could have, another, maybe I could have another rhombus here and have a plus here and here, minus there and there, and this would cancel and this would cancel. So could one fill this out in some clever way so that the interior dependence cancels and you end up with a functional that only depends on lambda, mu, and nu, which you know therefore is positive? And the answer is that the puzzles exactly do that. So that's the genesis of them. It was to solve this linear programming question about taking this polytope in like n+1 choose 2 dimensions, project it to 3n dimensions. What are the defining inequalities on that projection? It's the linear combinations that are suggested by adding up the rhombi you see in puzzles. Meanwhile, Kleotchko solved the same problem, but with Schubert calculus, and then we figured out that they were directly related. Okay, so maybe I should be a little bit more precise as to how those things relate. So if I have some not very large puzzle, let's get ourselves a puzzle. Okay. Then the way I know to take this and get myself an inequality on lambda mu nu, this one's telling me that lambda 2 plus lambda 3, I'm looking where the ones are, plus mu 2 plus mu 4 is, I think it's less than equal, that's the part where I sometimes mess this part up, less than equal to nu 1 plus nu 3. So if you have, so C lambda mu nu not 0 implies this inequality, okay? And not 0 implies this inequality, okay? And what we prove is that if you have this stupid equality, and so if you take some lambda mu nu and you check that equality and you check all the puzzles, then this will in fact be non-zero. So that was our main theorem about the puzzles. The thing one could then ask is, so that's an if and only if statement, but is it as tight as could be? Do you need all the puzzles, or could there be a shorter list of puzzles? For example, if I want to tell you that I'm thinking about a point inside the first quadrant, I could say, oh yeah, x is greater than or equal to 0, and y is greater than or equal to 0, and x plus y is greater than or equal to 0. That list of 3 inequalities is if and only if for describing this quadrant, but it's not the minimal list. Of course, the problem is that this third guy doesn't intersect the feasible set in codimension 1. It intersects it in codimension 2. So you don't want to see that one. And the answer is that a puzzle will define an equality in the minimal list if and only if that puzzle is rigid. If so we we only need the puzzles that are unique with that given boundary. And I haven't mentioned yet that there's this sort of recursive structure on what's going on here. So I have 2 different things that compute the same numbers, Littlewood-Richardson coefficients. You know, I said I could think about them this way, or this way, or this way. I've got this way. I've got these 2 different ways, and one of them is constraining the other. And you find that's actually giving you a recursive way of determining when one of these things is not 0. So stated that way, I'm particularly interested in when a Littlewood-Richardson number is 1. So I want to show you the smallest examples where it's not 1. So here they are. So this guy right here is what it's computing is half of C of this times that, and then get this coming out is 2. So there's 2 puzzles with the same boundary, and there's one of them, and here's the other. And you might notice that this one has this nice blue hexagon in the middle, and this one has this nice red hexagon in the middle. So what we observe towards trying to figure out when a Littlewood-Richardson number is 1 is let's orient. So let's decide that to break up the puzzle into regions according to what kind of puzzle piece is used. So I've got this region that's solid 1s, this region that's solid 0s. And aside from that, in this little example, I've got just individual pieces being their own regions. Let's orient the edges clockwise around the 1s and counterclockwise around the 0s. There should be, there we are. And this guy shouldn't have, right? Oh, no. This was, there we go. Okay. And the theorem is, this is me and Terry Tao, and in this paper, Chris Woodward's also on it, is that a puzzle is rigid, i.e. it's got the only, unique given its boundary, if and only if it has no gentle loops in this digraph. So you could imagine driving along these edges, and at any given time, there will be rhombi on one side of you, and there will be either all 0 triangles or all 1 triangles on the other side of you. And as you're driving around, I'm going to forbid you to make sharp turns like this. Okay, you're only from here, you're only allowed to turn like that. So that's what I mean by gentle. And then we prove that that the gentle loops are what's giving you some freedom. And the way we prove it is around a gentle loop. So I only tell you one direction, but around a gentle loop, you can take out a region of thickness 1 around that loop and flip the loop and put it back in going around the other direction. So we use that to prove if there's a gentle loop, then here's another puzzle for you. Okay. So here's an open problem in algebraic combinatorics. Is the set of puzzles computing a fixed C lambda mu nu connected by breathing these gentle loops. So we didn't prove this. We just know that if there's a unique such puzzle, if you have a puzzle and you can't breathe a gentle loop in it because there's no gentle loops, if there's a puzzle, then it's the unique one. And if there's a otherwise there's more than one. David?
So this oriented graph you're drawing looks a lot like Posterkoff's alternating strand diagrams, in that you have white things, the 0 regions that you go clockwise around, black things, the white regions that you go counterclockwise around, and another thing that you go alternating around. Does this mean anything?
Not to me. I will point out it predates that paper. Okay. Sasha also noticed this. Is this an efficient way for figuring out whether the number is 1? So kind of the question would be, if it's 1, can you quickly find the puzzle and then look at the puzzle and say, oh, no gentle loops? So certainly the second step is really quick. The first step, in practice, yeah, you just start filling in and you'll find that unique puzzle. But I had somebody look at this 20 years ago now as to the question of, if the puzzle is unique, will you greedily find it, or will you have to be a little bit, will you have to backtrack sometimes? And the answer was, you do have to backtrack sometimes. So I don't know about the efficiency thereof. Any questions, right? Zach? Everyone. Yep. So if there are multiple puzzles, every one of them has gentle loops, that we don't have this guy and this isolated from everybody else. And so I'm sure they're connected, but I don't know whether they are. Igor. I can repeat your question, Igor.
You want a mic? You can repeat your question. Oh, his voice is sorry. I'm sorry.
Reply to Sergei's question. Christian Nickenmeyer found the polynomial time algorithm to decide whether little Richardson coefficient is k for all k.
David.
Is the connectivity another OPAC?
Is C lambda mu nu equal 1? The high polytope is 0-dimensional. Yes, this was Fulton's conjecture, and we prove it using this characterization. So the so if this thing is 0-dimensional and you replace lambda mu and nu by n lambda, n mu, n nu, which on the partition level means you scale your partitions horizontally, then it'll just scale up this polytope. So if it starts out being a point, it'll stay a point, and the numbers will stay 1. If it's otherwise, the numbers start to increase. But we wanted to know if it was ever 1, does it stay 1? And it's easy enough to take these and think what happens when you scale lambda mu and nu, and your original puzzle with no gentle loops dilates to a big puzzle with no gentle loops. So that's how we proved that. Yes, that's the same question. So I'm not repeating it. Okay, so here's a related question, or just C lambda, but you allow different possible nus. But now I'd want to also breathe gentle arcs. So if I have some arc where I manage to drive from the south side to the south side, you can imagine breathing that and changing your nu. And of course, it's very interesting to think not just about a single coefficient, but to think about multiplying two classes and saying, can I understand what are all the things I get when I multiply two fixed classes? And so it's a different question and open. All right, so I want to tell you about two-step puzzles where there's a similar question. Then I'll tell you why. So here, I think the question was so interesting about knowing when C lambda mu nu is 1, because it tells you exactly the inequalities on when these things are non-zero by that inductive recursive procedure. There's also a Hermitian matrix version of this question where the numbers you see here are the eigenvalues of Hermitian matrices. So what this is saying right now is if you have two 4x4 Hermitian matrices, and the first guy has eigenvalues lambda 1 down to lambda 4, which are now real numbers, and the second one is mu, and their sum has nu, then this inequality holds for the spectra of those three Hermitian matrices. So we'll come back to that idea in a minute. So I want to generalize this question to a slightly harder one, but still apparently solvable. Which is to think about the cohomology of flags of a J plane inside a K plane inside Cn. So this guy is, it's not the full flag manifold, it's what we call a two-step flag manifold, these being the two steps. So this is the set of pairs Vj and Vk, and this one's supposed to be inside that one, and they're inside Cn. And that's what I want to understand the cohomology of. So this guy again has a Schubert basis, and I'm going to go straight ahead and skip past anything like partitions and say I want this basis to correspond to words, to strings with content 0 to the j, 1 to the k minus j, 2 to the n minus k. So we need 3 different letters now instead of 2 letters like we had in the Grassmannian case. And so once I learned this interpretation of Littlewood-Richardson coefficients and learned that the full flag manifold case where one has all steps instead of just 2 steps was unsolved, I said, well, maybe puzzles will do it. And I started looking for what the smallest puzzles would be that I would need, smallest puzzle pieces. And I said, well, I think I know I want these. It turns out to be good to take the rhombus and cut it in half. And I'm going to have a new edge label. So I'm going to only work with triangles now. And so that's good. But the bad thing is that I'll have these edge labels that you don't get to use on the boundary of the puzzle. On the boundary, you may only use 0s and 1s and 2s. And 10 doesn't count as a 1 and a 0. It's a new kind of label. But I also want these 2s apparently. So that suggests that I should have things like this and that. And if I were in some silly cases here where like j were 0 or j were k or k were n, then that would reduce to I'm only going to use 0s and 1s or 1s and 2s or 0s and 2s. So that's why it seems good to have the 2-step puzzle rule reduced to the 1-step puzzle rule. Turns out you need 2 more pieces. That one and that one. Okay? And then the theorem is that, so let me be clear on the order of things here. So my conjecture from 99 was that C pi rho sigma is the number of these puzzles with these pieces for the 2-step flag manifold. Okay, and then that was proven 15 years later. Well, published 15 years later, proven, I don't know, 6 years later or something, by Book, Kresh, Perbu, Tamvakis. And I'll say in a minute why they cared about the 2-step case. So in fact, I didn't circulate this conjecture to many people because I had there's a way you can imagine generalizing this to 3-step or n-step. And I thought it was pretty great and circulated to a few people, then checked out the conjecture by computer, which is what I'm glad I didn't do first, as it turns out. And it was wrong for 3-step. And so then I said, okay, well, if it's wrong, it's wrong. What am I doing with this? I shouldn't bother trying to prove it for 2-step. It probably like fails at some large n or something. But for reasons I'll explain in a minute, Book, Kresh, and Tamvakis really wanted to understand the 2-step case, even if they couldn't understand the full flag manifold case. Okay, so it's easy now to state the OPAC question though. How to characterize rigid 2-step puzzles. So if you have a puzzle made out of these, and I won't bother drawing examples because I think you have that power now. If you have a puzzle made out of these, then how do you look at it and do something like the gentle loop considerations to figure out whether it's the unique such puzzle? Yes? That's what I'm taking as the definition. So I'm asking,
Repeat the question.
right. So, when is C pi rho sigma equal to 1 in the 2-step case? So, so that's where I'm heading. Okay.
Repeat the question.
No, I'm heading there. So the point is going to be though, okay, so why, one way to jump ahead and say why BKT we're particularly curious about 2-step and if you could get this, if you could characterize this in 2-step, what would it tell you? So I told you a couple of minutes ago that with the one-step ones give you the solution to this Hermitian matrix question of what inequalities hold on the spectrum of the sum of two Hermitian matrices. Now, there's a harder question than that, which is where Terry and I started and gave up and retreated to the Hermitian question. The harder question is, if you have two special unitary matrices and you know their spectrum, what can you say about the spectrum of the product of those two special unitary matrices? And if your special unitary matrices are very nearby the identity, then you're basically doing addition, and it reduces to the Hermitian matrix question. So we know, in fact, what the inequalities are that determine, that characterize the possible spectra of products of unitary matrices, and it's not exactly solved by the two-step puzzles, but I'll say how they're related. So definitely, if we could solve this last OPAC I wrote down, then we would have a combinatorial way of listing exactly the inequalities that determine the spectrum of the product of two unitary matrices. Yeah. So does this rigidity have to do with the matrices themselves? No, I don't think so. I don't. No, I mean when we have something here where it's not rigid, then it's telling us an inequality on matrices that we don't care about it because we can derive from others. So it's not really about any single particular triple of matrices. Okay. All right. So I want to tell you all sorts of things, but I will limit myself right now to, I don't think I have time to include this, so I'm not going to define this thing, which is fusion coefficients. C lambda mu nu, whoops. C lambda mu nu L, okay? And what I will say about these is, so some properties these have, they have some representation theory meaning that lets you know they are non-negative. So one way you can get a hold of the representation theoretically is about tensoring quantum group representations at a root of unity. The root of unity is defined in terms of L. Because it's at a root of unity, it's not about the quantum parameter heading towards zero. So there isn't as far as I understand, there isn't a crystal graph theory or crystal theory of the representation theory that one would want to do here. But one nonetheless has some representation theory interpretation of it. These are also increasing in L, and as L goes to infinity, these guys are just the usual Little-Richardson numbers. Okay, and so these are dominant weights of some semi-simple group. And I'm emphasizing that because in a moment I'm really going to want them to be from like SLN, not GLN. So we have these multiple ways of computing this. I wrote down 3 of them. Let's focus on the first one, which was the hive. So we had this polytope of hives, and it was defined by a bunch of inequalities. And now, because of these 2 conditions, I know that there's some there's some smaller number I want to compute, and so this is a little unfortunate that I'm stating this question without having defined the fusion coefficients. But I will say you can look it up, and there's this open question, which is to give a polyhedral interpretation of C lambda mu nu L. So I will give you a way to compute these right now, even though I won't define them, but it'll be a way to compute them. And then you can ask, so you will be able to approach this question, even though I don't define where they come from. And two of the questions will be this one, and also why is the definition I'm about to give you increasing in L? Okay. So to compute C lambda mu nu of L. So here lambda mu and nu are dominant weights for SLK. And so what does that mean? It's decreasing sequences up to adding the all ones vector. So if I knew this, that would tell me, well, give me a representation of GLK. But if I added all one to that, it would be a different representation of GLK. How so? Because it'll have been tensored by determinants. Once I go to SLK, I can't notice that tensor by determinant factor. And so that's why I'm only getting something up to there. Okay, so I lift lambda mu and nu to actual sequences. Lambda tilde mu tilde nu tilde. Okay, there's a problem now, which is that probably the number of the area of this is not the sum of these two areas, because I just lifted them in some arbitrary way. So I want to measure that. Okay. So if we can fit these in a box of size this, then we say that they are level L representations. So for any given L, there's only finitely many lambda mu and nu to consider. So for GLK, ordinary tensor products story, there's infinitely many representations, questions to ask. This is a little bit more like the Grassmannian case, where you only have finitely many questions to ask. All right, so let's let lambda tilde plus mu tilde minus nu tilde, that will be k times s. So if C lambda mu nu is not 0 on the SLK level, then there must then the center of the SLK has to be acting in this coherent way, like I was saying before in the bottom right corner of the hive. The corresponding thing here is that this difference has to be a multiple of k. All right. And now, now C lambda mu nu at L is the coefficient. So there's going to be two parts of this definition. It's the coefficient of S nu in S lambda times S mu times S, an entire row of width L raised to the, this is a bad choice. How about I take T here? Raised to the T power. But in the quantum cohomology, not the ordinary cohomology. So I also need to tell you how to compute in quantum cohomology. And there the statement is that C lambda mu nu in quantum cohomology of the Grassmannian is the number of two-step puzzles where we don't put lambda and mu and nu here. We put lambda here, but the last D zeros and the first D ones are turned. We get the first D2s are turned into ones, and here the same thing. Last D zeros and the first D2s are turned into ones, but here it's the opposite. The first D zeros and the last D2s are turned into ones. So here, lambda, mu, and nu, I want their content to be 0 to the k, 2 to the n minus k, with no ones at all. And then some zeros and twos turn into ones. And D here is lambda plus mu minus nu is n times D. So where did this thing come from? Oh, this theorem is a book, Kresh and Vakis. So these guys wanted to understand quantum cohomology of the Grassmannian, which is something about curves in the actual Grassmannian. Instead of taking a triple intersection of Bruja cells and getting points, they say, I'm gonna allow myself to walk from one Bruja cell through another to a third using some curve. They take that curve of some degree D. It's a family of K-planes, and they say, let's intersect them all. And they end up with a K minus D plane typically, and add them all. They end up with a K plus D plane typically, and they end up with a point inside a two-step flag manifold, which is why we're doing two-step stuff here. And in this way, they magically reduce understanding quantum cohomology of Grassmannians to ordinary cohomology of two-step. Sammy. They totally do it geometrically. They, I mean, and then they say, boy, wouldn't it be nice if somebody knew how to do two-step? Wait, didn't Alan send us this conjecture some decades ago? We hope that's correct. And then they spent some more years and recruited Kevin to prove that my two-step conjecture was correct. But they did totally geometry before that. All right, well, now you have a way of computing this. It goes through quantum cohomology, which in turn goes through two-step puzzles. And so if you knew when the two-step puzzles were one, that would solve this quantum cohomology question. And it would give, thanks to work of Belcale, the minimal set of inequalities on this unitary matrix question. But also, you can measure this for each L, and you get a very different looking set of puzzles. Like the D and the S, the D and the T change as you change this L, and I don't know how to compare those puzzles. In particular, I don't know how to see that I get more puzzles when I increase L. If one could do this, then one could embed the puzzles the puzzles one thinking of into a larger and larger and larger set, and eventually compare it to the standard set, and then hopefully say that's those we can biject with hives. So we're not supposed to get all the hives, but only hives satisfying a bunch of inequalities. And I had a whole other topic that I won't tell you anything about. 7 minutes? Oh, that's plenty. All right. Yeah.
Is there a semi-group property on the support of quantum homology of Grassmannian?
Is there a semi-group property for the quantum homology of the Grassmannian? I think the point is, I think the point is you need to add your lambdas, mu's, and nu's and your L's. So I'm answering the question for the fusion coefficients instead of the quantum homology of the Grassmannian. But I think then that's true, as long as you add the L's as well. Oh yeah. No, I mean there's only finitely many to talk about. No, yeah. Yeah. Okay. Now for something completely different. Consider the following polynomial. Let's take this matrix. It'll have ones down the diagonal, and it'll have variables up here, and it'll be 0 here. And I want to take the product of the northwest determinants of this. So this entry, this 2 by 2, and so on. And I get some polynomial. And let's do the n equals 3 example. So if I've got a, b, c, 1, 1, 1, then my function will be a times times bc minus a. And maybe times -1, but I don't care about the signs on this thing. Okay, what I'm going to do with this is generate an ideal with it. So, and then start, or think about the vanishing set of this, and starts to decompose and intersect and decompose and intersect and see what things I get. So I start off with imposing neither of these equations. And then I say, let's impose this one or this one. So that's that I took the vanishing set of this and I decomposed it into these 2 pieces. Or if you like, I took this, this non-prime ideal and saw it as an intersection of 2 prime ideals. And then I'll add those ideals together, which is to say I'll impose both equations. And I find out, well, now A is 0 and BC is also 0. So B or C are 0. So I end up with A is 0 and B is 0, or A is 0 and C is 0. And then I intersect, and that now doesn't break any further. Okay. So anybody recognize this poset? Okay. So this is the Bruchau order for S3. And theorem, if you do this for n by n matrices, and you do this recipe I'm telling you of decompose, intersect, you will get one stratum for each permutation that you'll get exactly the Bruchau order for Sn. So what's the general setup? When do I expect things to be nice here? And I've got questions about it. So I want to consider polynomials in n variables of degree n. It's a little bit too strong, but it'll be fine. Such that the leading term is just the product of the variables. Okay, so here what do I mean by leading term? I mean, let's go, for example, in this case, lexicographically from the northeast. So whenever I have one of these determinants, I'm first going to meet it in its northeast corner, and then I'll get that times what's left over, and then meet that in its northeast corner, and I'll end up getting the product of the anti-diagonals of these determinants, and that gets me every variable exactly once. So I get this times that. The leading term here is the product of the variables. Okay, so theorem, if you intersect and decompose, starting with such an f, all your intersections are reduced. So you don't end up with some tangencies where where it's kind of curious, schemally what sort of things you're going to meet. So you get some reasonable kind of set theory going on here. And what does leading term mean? Whatever you want it to mean. Pick some weighting on your variables, maybe lexicographic or maybe something else. For any choice of how you want to weight the variables, such that this is the leading term, this will happen. So maybe instead of leading term, I'll call this init f. Okay. So too is init y for any y in the stratification. So if I have some ideal and I say, let's pick out in that ideal, let's pick out the leading terms of the polynomials in that ideal. So like I would pick out this, it doesn't do anything interesting to the rest of them. Then I'd say, well, I go to init y, so I replace this with bc equals 0. And I would get some reduced ideal. If you pick your weighting on your variables generic enough, then whenever you take the leading form of some polynomial, one of the monomials will win and will beat all the others. So you won't have ties if you pick your weighting generic enough. And then what this says is you'll end up with a Stanley-Reasoner ideal, one generated by square-free monomials. Yes. No. And so here's the sort of question I'm curious about. What can the poset of strata look like? And it helps, especially if each variety encountered is normal. So I'm a little sad to include a condition like that, since it's not so much a combinatorial condition, but I think I better stop there anyway.
Are there further questions for Alan?
Yes, sir. So is there some interpretation for the individual vertices of the honeycomb or the hive, as I was doing it here? So the best answer to this is in work of Joel Kamnitzer, building on ideas of David Spire. At least he's still here. I don't know if Joel's on the Zoom. And there's a very clear interpretation of them individually, but everything's happening inside the affine Grassmannian. So the way he's getting a hold of what C lambda mu means is via geometric syntachy.
I have a slight point. So most triple intersections of Schubert varieties that have finally many points, you find they have the full Galois group as their
all of them, the Galois group acts transitively.
Yeah, it always acts transitively, and often it's the full symmetric group. So you're unlikely to have be able to associate something to a particular point.
Yes.
Answer to this question, tractable, but somehow
not kind of completely, I'm not, maybe some people are not quite satisfied with this question. Also because basically it's kind of a reducer rule, question whether a little malicious application is not zero, the question whether a little malicious application is not zero. Or one.
Well, there's
But
two.
kind of reduce this question to the same kind of question, maybe for a smaller size, that kind of repeat it, but is there some hope to kind of make a non-inductive?
Well, I would say that there's two answers here. So one of them, I mean, what? So is there a non-inductive way to get a hold of the C lambda mu nu instead of going being non-zero, instead of going through the Horn recursion that relates that gives you inequalities at level n using puzzles at level k for all k less than n. So what saturation gets you is that the number is not zero if and only if the BZ polytope is not empty. And that is now a linear programming question. And so that's polynomial time, so you could decide for yourself whether reducing something to linear programming is enough answer for you.
Okay, maybe actually, but it's still kind of not analysis is factor because you reduce question to the same kind of question.
Well, a smaller version of the same kind of question. Well, one thing I'll say is that so we have this cone, and the question is, are we in this cone? And and what the puzzles tell you is the interesting inequalities on this cone. So there's these stupid inequalities that say lambda 4 is greater than or equal to lambda 5. And those are actually the most difficult to deal with, it turns out. And then but they're easy to write down, but you want to stay away from those. And then the interesting ones are the ones from the puzzles. So that's a facet description of that cone to see, are we in there? And then like one thing you might ask is, could we get an edge description of that cone? And Balkali has some work on that, and it's painful to try and generate that cone. And I think he's only thinking about the edges, like generating it rationally, not even worrying about the difficulty of generating it as a semigroup. Vic? So are there puzzles? Oh, okay, and then you read. So basically, we don't have puzzles for any multiplication. What we have puzzles for is in terms of multiplication problems is for 1 and 2 step flag manifolds and we can do in fact equivariant K theory. I didn't talk about either of those. 3 step where we can do K theory but not equivariant. And that's not quite it. We have some other type A stuff, and also with Eva Halacheva, and I should say that some of the puzzle stuff is joint with Ray Tao. The stuff I'm talking about right now is joint with Paul Justin, and the thing I'm about to mention with Eva was about not a multiplication rule, but about branching from the restriction map on cohomology from the Grassmannian to a symplectic Grassmannian contained within. So we've got puzzles for that. But now what the question is more like, what if you have the symplectic Grassmannian embedded in its square and you want to restrict classes from the products to the diagonal? That's multiplication. And we don't have any puzzles for that. So we have a bunch more type A stuff.
Yeah, there's sort of an analog of Horn inequalities for that, but it's not particularly satisfying.
Okay.
Sorry, Kevin. Any other questions?
Anton? Yes, and that's exactly how this work of Belkale and is there a connection between the unitary connections versus stable bundles on P1 with parabolic structure. And it is that connection that Agnihotri and Woodward exploit to reduce the question of the unitary matrix product question to quantum Schubert calculus. And so they get the wimpier version that says every inequality on the unitary problem can be blamed on some quantum cohomology coefficient being non-zero. And Belkale cuts it down to actually you only need when they're equal to 1. And both of them are thinking about parabolic bundles on P1.
Okay, well, I think we should thank Alan again. And